Right, so let's look at another hypothesis testing case where we will have a detailed situation. People entering an exhibition have to decide whether they turn right or left. The people organising the exhibition want to know whether there will be a preference for one of the directions. A trial run is done using 20 people, and it's found that 15 went to the left. At 5% significance, does this mean that people have a preference for a particular direction? So now the preference may be in either direction. It doesn't say right or left. It doesn't therefore negate people went to left. So we therefore have a situation where we've got a two-tailed hypothesis test to conduct. So let's set one up. First, we have to define P. So let's define P. Let's say let P be the probability that a person turns left. Probability that a person turns left, and then we can now set up our null hypothesis as it being P equals 0.5, and we're saying that there is an equally likely chance that they turn right or left. Alternative hypothesis is that there isn't an equally likely chance. Then we're testing to see if there's a preference in one direction. So therefore, from here we know it's going to be a two-tailed test. Right, so given it's two-tailed, let's see what we've got. The significance level in the question has been given to us as 5%. And so therefore, our 5% divided by 2 will give us 2.5% on either side. And that obviously is 0.025. Let's now define x. So I'm going to say let x be the number of people who turn left. And we can therefore say that x, if h0 is true, let me just let's put that in properly. So let's say if h0 is true, and then p equals a half, then x is going to be binomially distributed. From the question, we know we've had 20 people, so n would therefore be 20, and p is a half. Now, we have two methods again. We can either just compare the probabilities either side and conclude that way. So let me do that method first, and then the second method is where we have to find the actual critical regions themselves. So let's method one, let's use probabilities. Okay, and in this method, 15 went to the left, so the probability that x is greater than or equal to 15. We're looking at the upper tail is 1 minus the probability that x is less than or equal to 14, which from the tables is 1 minus 0.9793, which equals 0.0207. And we simply can compare that value and say that the 0.0207 is in fact less than 0.0025. So the probability that x is greater than equal to 15. Oops. Again. Right, so the probability x is less than or equal to 15. So maybe a mistake there, let's do that again. So it's greater than, right, probability x is greater than or equal to 15 gives us 0.0207, which is less than 0.025, and since it's less than, we can reject H0. So we reject H0 given that it's now, it seems like it's in a critical region because it's less than 0.025. We reject H0 and conclude that there is sufficient evidence to suggest that people have a preference for a particular direction. So that's one method. Another method we can use, obviously, when you've got to find the actual critical values which make the boundaries. So let's do method 2. To do work out the actual regions involved, and in here we've got obviously for 2.5%, we've got x is less than or equal to a is less than 0.025, and we're looking for the highest value of a. And the probability that x is greater or equal to b is less than 0.025, and here we're looking for the lowest value of b. So let's do the part A first and go to the tables. Right, so we want a value of it on the lower end, which is less than 0.025. We can see straight away that that's going to lie between 5 and 6. And we want on the upper end a value which is going to turn out to be greater than 0.95 and sorry 975 since it's 25%, and that should lie somewhere between 13 and 14, so you've got 975 over here. Okay, so let's return to this once we've done the calculation. Right, so from the tables we can see probability x is less than or equal to 5 gives us 0.0207, which is less than 0.025, and we can also see that the probability of x is less than or equal to 6 is 0.0577, which is greater than 0.025. So obviously when x equals 5, we have our critical value. So when x equals 5, we have a critical value. And this forms the, this determines the critical region. So x is less than or equal to 5 is therefore our critical region. What about the other end of the spectrum? So where we've got probability x is greater than or equal to b, we're looking for the lowest value is less than 0.025, and that's the same thing as saying 1 minus probability x is less than or equal to b, take away 1, less than 0.025. And so it's one takeaway, the other part of the distribution. And if we were to rearrange this, we'll get x is less than or equal to b, take away 1 is in fact greater than 0.975. From the tables, if we go back to the tables, 975 we know lies within the region of 13 and 14. We've got x is less than or equal to 13 equals 0.97423. The probability that x is less than or equal to 14 equals 0.9793. And so it's greater than 975 when we have 14, so therefore b minus 1 equals to 14, and b will therefore give us 15. So on the upper end of the distribution, we know our critical value is when x equals to 15, and the critical region is when x is greater than or equal to 15. And so we've got a value of, if you go back to the question, where 15 people turned left, and so we have 15 people went left. So therefore, x equals 15 lies in the critical region. And therefore we reject x naught. And so therefore we can conclude there is evidence to suggest that people have a preference for a particular direction. If we look at the tables, this is what we've got. We can see when x equals 15, the critical region starts. Okay, and when x equals 5 is when it's on the lower end of the tail. And so we've got x equals 15, which lies in that critical region, and therefore we reject our h naught.